Hi everyone, today a video in the Equilibria series looking at the equilibrium constant and changing conditions. So we looked in the previous video of this series at an equilibrium reaction, a reversible reaction. And if we have a reaction that reaches an equilibrium, that's where our proportions of reactants and products don't change, but we don't have 100% reactants or 100% products, we can actually write a mathematical expression for this equilibrium reaction. And the expression that we write is the concentrations of our products divided by the concentrations of our reactants. So if I have a simple reaction, A plus B goes to C plus D, the capital letter indicates the species, and the small letter indicates the stoichiometric ratio. So it could be, for example, we have 2A plus 3B going to 4C and 2D. The small letter just represents the mole ratio. So my expression for this, my mathematical expression, would look as shown as there in the middle. So the concentration of C raised to the power of C, the concentration of D raised to the power of D, concentration of A raised to the power of A, concentration of B raised to the power of B. So it's always our concentrations raised to the power of their stoichiometric coefficients, raised to the power of essentially the number they have in front of them. We also have the subscript EQM. That just tells us that it's an equilibrium reaction. Typically, we don't include the EQM subscripts because if we're writing this expression, we know that it's an equilibrium reaction, and so we don't really need to write it. But that expression of our concentration of our products divided by the concentrations of our reactants is constant provided the temperature is constant. And this constant is called the equilibrium constant. It's given the symbol Kc. Now, the key thing here is that it's a capital K, a big K. Remember that a small k represents a rate constant. A big K represents an equilibrium constant. And so the expression above is the equilibrium constant, capital Kc. Now this expression can be applied to any reversible reaction. And the value of Kc is different for different reactions, but the same and different for the same reaction at different temperatures. So if I have my reaction shown above, A plus B goes to C plus D, that will have a particular equilibrium constant that we can calculate by writing that mathematical expression. And for that reaction at different temperatures, the equilibrium constant will be different. Now, the units for Kc vary, and they must be worked out for each reaction by cancelling out the units on each term. And the value of Kc is found by experiment for any particular reaction at a given temperature. And as I said, the equilibrium subscripts can often be omitted unless the question specifically asks for them. And so if we just look at an example here of calculating what our unit for Kc would be, the key thing is to remember that concentration is in units of moles per decimeter cubed. And so here's a sort of example reaction. I have my A plus B going to C plus D reaction. So if I write my Kc expression, it's always the concentration of products divided by concentration of reactants, and I raise those concentrations to the stoichiometric coefficients. So let's imagine I have a reaction that is 2A plus 2B going to C plus 2D. My Kc expression, therefore, looks like is shown in the middle. Concentration of C multiplied by the concentration of D squared, because there were 2D in the equation, divided by the concentration of A squared and the concentration of B squared. So, remembering that the concentrations are in units of moles per decimeter cubed, we therefore on the products line, the top line, have mole per decimeter cubed multiplied by mole per decimeter cubed squared. So essentially, mole per decimeter cubed, there's 3 lots of them. On the bottom, we have mole per decimeter cubed squared multiplied by mole per decimeter cubed squared. That's the same as having mole per decimeter cubed to the power of 4. 4 lots of mole per decimeter cubes. And so if we have 3 lots on the top, 1 lot on the bottom, we can cancel out 3 from the top and bottom. That leaves us with just 1 mole per decimeter cubed on the bottom. However, we can't have this reciprocal unit, so we write it up at the top. And to do this, we just essentially flip the signs of our of the powers that we've raised it to. So 1 over mole per decimeter cubed is exactly the same as mole to the minus 1 decimeter cubed. So we've gone from mole to the power of 1 to mole to the minus 1, and decimeter to the negative 3 to decimeter cubed. That's the way that we work out our units for Kc. I wouldn't bother trying to remember if you have particular ratios what the units are. It'd be too much to remember and you're very likely to make a mistake. Instead, write out your expression for Kc, write out the essentially how many mole per decimeter cubed you have on top and bottom, and then just go through cancelling. So we can actually calculate the value of an equilibrium constant, Kc, from knowing the concentrations and sometimes the moles that we have in our reaction. And so there's a simple mathematical procedure for calculating the value of Kc for a given reaction and working out the mole quantities at equilibrium. So I'm going to go through an example of the way that I would do these types of questions. So let's say the question is this. 0.2 moles of ethanol is mixed with 0.2 moles of ethanoic acid and allowed to reach equilibrium. The total volume of the system is made up to 25 centimeters cubed by water. Remember that 25 centimeters cubed is the same as 0.025 decimeters cubed. To convert from centimeters cubed to decimeters cubed, we divide by 1,000. Now, by titration, it is found that 0.05 moles of ethanoic acid is present once the equilibrium is reached. So, from that last bit of data, the 0.05 moles of ethanoic acid at equilibrium, we can actually work out the numbers of moles of the other components. And so the way that I do this is kind of set it out as a sort of table underneath the reaction. So I write my reaction equation, which is ethanol plus ethanoic acid. It's a reversible reaction, so remember we have to denote it with this kind of double half arrow, one going one way, one going the other way, a reversible arrow. And then this produces our ester, ethyl ethanoate in this case, and water. Now again, like I've said in previous videos with mathematical questions on, we don't have to actually understand the chemistry. So even if the reaction they give you is an unfamiliar reaction, we don't have to understand the mechanism of this, we don't have to understand really the chemistry of how this works, we're just dealing with the numbers. And so the way that I set this out first of all is to write down what were my moles at the start of the reaction. Now sometimes they'll give you these mole values, sometimes they may just give you the concentration and the volume you started with, and you have to work out the moles by using N equals C times V. In this case, we were given the moles, and so it's very, very simple here to just write them down. So we had 0.2 moles of the ethanol and 0.2 moles of ethanoic acid. And obviously at the very start of reaction, we have no moles of our products, so no moles of the ester and no moles of our water. Then we were told that 0.05 moles of ethanoic acid is present once equilibrium is reached. So under the ethanoic acid sort of bit in my table, I'm going to write 0.05 moles. Now what I have to do is look at the mole ratios. And like in many, many types of questions like this where we're dealing with calculating moles and calculating concentrations, we always have to look at the mole ratios. I have a 1-to-1 mole ratio between my reactants. So 1 mole of ethanoic acid reacts with 1 mole of ethanol. So if there are 0.05 moles of ethanoic acid at equilibrium, there must also be 0.05 moles of ethanol, because it's a 1-to-1 ratio. However much ethanoic acid there must be the same ethanol. So there's also 0.05 moles of ethanol. Then we need to look at our product. So we started, remember, with the reactants of 0.2 moles. And we've, at equilibrium, got 0.05 left. So that means that we must have used up 0.15 moles. We started with 0.2, we've ended with 0.05, that's a difference of 0.15. So 0.15 moles of our reactant must have reacted to form the products. And again, we need to look at our mole ratios. We have 1 mole of reactants producing 1 mole of products for each reactant and product. And so, therefore, if we've used up 0.15 moles, we have a 1-to-1 ratio, and so therefore the moles of our ester is 0.15 moles. And likewise, the mole ratio between the ester and the water is 1-to-1, and so we also have 0.15 moles of water. So the key thing is to always look at the mole ratios. Now, remember our Kc expression, we can write this out, and I have at the bottom concentration of products divided by concentration of reactants raised to the stoichiometric coefficients. Here, everything's a 1-to-1 mole ratio, so everything's to the power of 1. We don't have to write it if it's to the power of 1. And so our Kc expression is our concentration of the ester, concentration of the water, divided by the concentration of ethanol and the concentration of the ethanoic acid. Now the key thing here is that it's concentration, not moles. So we have to convert our moles into concentrations. So we use our N equals CV equation. We rearrange for concentration. That's the moles divided by the volume. And the key thing is to remember that concentration is moles per decimeter cubed. Volumes are typically given in centimeters cubed. And so we have to convert our volumes from centimeters cubed into decimeters cubed by dividing by 1,000. Or we can use the other form of this expression, which is that it is N equals C times V divided by 1,000. And therefore, our concentration is N times 1,000 divided by the volume. So we can calculate the concentration for the 0.15 moles. This is for the concentration of the ester and the water. We have 0.15 moles. We divide it by our total volume of the system, which we were told was 25 centimeters cubed, times by 1,000 to convert it, and we end up with 6 moles per deciliter cubed. Likewise, we can do the same calculation for our 0.05 mole species, that's both of our reactants, and the concentration there is 2 moles per deciliter cubed. So now we have our concentrations. We simply put these concentrations into our Kc expression, and when we do that calculation, we find that our Kc value comes out to be 9. Now again, note the use of significant figures here, as we've noticed in other mathematical videos on this channel. We have to look at our question, see what the minimum number of significant figures is. Our total volume is 25.0, that's 3 significant figures. However, the moles, the 0.20 and the 0.050, are both 2 significant figures. And so therefore we have to give our answer to 2 significant figures, 9.0. We also have to work out our units, remember. So we have 2 lots of mole per decimeter cubed on top, mole per decimeter cubed squared, essentially. The same thing on the bottom, and so they cancel out to give Kc, in this case, having no units. So it is possible that Kc could have no units, but you always have to work out the units and double check that it is actually unitless, or whether it has units. So we can then also think back to changing conditions. And we've seen in the previous video that the Chatelier's principle states that when an equilibrium is disturbed, the equilibrium position will move in the direction to reduce that disturbance. It moves to oppose the change that has happened. And we can use this principle to predict the qualitative effect of changing conditions. Remember that the Chatelier's principle doesn't tell us anything numerical. It doesn't tell us how far the equilibrium moves. It can just tell us which way. And also we can see how that will then affect the value of Kc. So if we think about changing temperature, whether Kc increases or decreases depends on whether the reaction is endothermic or exothermic. But what we do know is that if our equilibrium constant increases, then the equilibrium is shifted to the right. Remember that shifting to the right means we've made more product. Our Kc expression is concentration of products divided by concentration of reactants. If we make that top line bigger, more products, we're going to end up with a bigger number of Kc. If the equilibrium constant decreases, then the equilibrium is shifted in the other direction, to the left, the backward direction, making more reactants. Again, remember Kc is products divided by reactants, and therefore, if we have our bottom line being more our reactants, we're going to have a smaller value of Kc. And so the general rule is that if we have an exothermic reaction, one that releases heat in the forward direction, if we increase the temperature, this will decrease Kc and our equilibrium shifts to the left. And a way to think about this is if I have an exothermic reaction and I increase the temperature, the equilibrium from Le Chatelier's principle is going to want to move in the direction that opposes that change. If we're increasing the temperature, it's going to move in the direction of reducing the temperature, i.e. taking heat in, and that's the endothermic reaction. Therefore, the opposite direction, the backward reaction. Therefore, we produce more reactants, and from our expression of Kc, with reactants being on the bottom, Kc decreases. And also the converse is true. If we then have an endothermic reaction increasing the temperature, the equilibrium is going to want to oppose that change. It's going to want to move in the direction that reduces the temperature, takes in heat. That's the endothermic direction, the forward direction. And so this produces a bigger value of Kc because we produce more products because our equilibrium shifts right. And so generally, if you're given an enthalpy change for a reversible reaction, the convention is that this always refers to the forward direction, from left to right. But if we have an exothermic reaction from going from left to right, from reactants to products, the reverse of that must be the endothermic reaction. We can just flip the sign of the reaction, flip the sign of the enthalpy change. And the key thing here is to remember that the equilibrium constant does not change unless the temperature changes. Now we can also think of changing concentration. The really key thing to remember here, as we said on the previous slide, was that Kc only changes when the temperature changes. So if we consider our reaction, A plus B goes to C plus D. If I add more A, if I increase the concentration of A, the application of the Chatelier's principle tells us that the only way to reduce its concentration is to react it with B. The Chatelier tells us that the equilibrium will move to oppose the change, to oppose this increase in the concentration of A by reducing the concentration of A, and the only way to do that is to react it with more B. And so therefore we end up producing more C and more D, more product. The equilibrium shifts to the right. And so eventually a new equilibrium will be set up that has more of the product. The position of equilibrium will have shifted further to the right. Now if we consider it mathematically, Kc always remains constant unless the temperature changes. So in the Kc expression, remember concentration of products over concentration of reactants, if I add more of this A, the concentration of A gets bigger, so the bottom of that equation gets bigger. But it reacts to form more of C and D, so the concentrations of C and D increase, which makes the top terms bigger. And actually what you'll find is that the amount by which these terms both increase is exactly the same. And so the overall value of Kc does not change. Even though we've added more A in, that's made more C and D, so we've increased both the reactants line and the products line, and therefore the value of Kc has not changed. So even though our equilibrium has shifted to the right, the position of equilibrium has changed, the overall value of Kc has not, unless the temperature changes. Now the size of the equilibrium constant can tell us about the composition of an equilibrium mixture. If Kc is a number much greater than 1, then the products predominate over the reactants and the position is far to the right. Basically what we're saying is that the concentration of products is much greater than the concentration of reactants. We have a much bigger term on top than on bottom in that equation, and therefore we end up with a number much bigger than 1. Now if Kc is much less than 1, reactants predominate over the products and the position is far to the left. So this is if we have lots and lots of reactants and not much products. Therefore our bottom term is much bigger and we're going to end up with a value much less than 1. Now catalysts have no effect on the value of Kc and the position of equilibrium. We talked about this in the previous video of this series. A catalyst increases the rate of reaction by lowering the activation energy, providing an alternative pathway, one with a lower activation energy. Because our reaction is not just a complete reaction, a reversible reaction, a catalyst affects the rate of both the forward and the backward reaction, and it affects it equally by reducing the activation energy for both reactions. And so they don't affect the value of Kc because they affect both forward and backward reactions equally. What they do affect is the rate at which equilibrium is reached. So if it normally takes 2 hours for this equilibrium to be reached, adding a catalyst might make it now 1 hour. Now reversible reactions can take place in the gas phase too. We've seen some examples of these in the previous video. We can also talk about pressure changes and how those affect equilibrium, but again remember that Kc only changes if the temperature changes, because changing pressure essentially is the same as changing concentration in solution. And so these equilibria also obey the equilibrium law, but their concentrations are usually expressed using partial pressures instead, and we'll see in the next video in this series that we can cover something called Kp. Essentially it's the same as Kc, it's just for a gas phase reaction rather than a solution phase reaction. We use pressures rather than concentrations. So time to have a go at some questions. We have some mathematical questions here at calculating values of Kc. So if you want to have a go, pause the video and the answers will be on the next slide. So the first question we had here was methane and water reacting to produce carbon dioxide and hydrogen. And we were told we had our initial moles, and to calculate the amount of moles of methane, steam and hydrogen at the equilibrium mixture. So I set out my table. I've been told that I have 1 mole of methane, 2 moles of water at the start of the reaction. Therefore I must have 0 moles of the carbon dioxide and the hydrogen. And then at equilibrium, we're told that there is 0.25 moles of carbon dioxide. So I'm going to write 0.25 under the carbon dioxide part. Now we have to use our mole ratios. I have a 1 to 4 mole ratio between the carbon dioxide and the hydrogen. Therefore, I times my mole value by 4. 1 mole of carbon dioxide, 4 moles of hydrogen. 0.25 times by 4 gives us 1 mole of the hydrogen. So the key thing is to use the mole ratios. 1 to 4 ratio times that number by 4. Then I'm going to look at my reactants. I have a 1 to 1 ratio between my carbon dioxide and my methane. And so if we were told that 0.25 moles of the carbon dioxide are produced, that must have meant that we've used up 0.25 moles of the reactant of the methane that's in this 1 to 1 ratio. And so if we've used up 0.25, therefore we must have taken 0.25 away from the starting 1 mole of methane, which gives us an equilibrium value of 0.75 moles of methane. And to work out the moles of water, 2 ways you can do this. The first is just to see that it's a 1 to 2 mole ratio between the methane and the water. So we can times the 0.75 by 2 to get 1.5 moles. The other way is to note that we used 0.25 moles up to get to our equilibrium amount of the CO2. It's a 1 to 2 ratio between the CO2 and the water, and so therefore we can times our CO2 value by 2. That gives us 0.5 moles, and therefore we must have used up 0.5 moles starting from our 2 moles, which again gives us 1.5 moles. We were then told the volume of the flask was 5 decimeters cubed. Calculate the concentration of methane in the equilibrium mixture. And so in order to do this, we're going to use the equation that the moles is the concentration times the volume. Rearrange the concentration, so moles divided by volume. We don't have to convert here because the volume was actually given to us in decimeters cubed. And so we do our 0.75 divided by the 5 decimeters cubed, and this gives us a concentration of methane of 0.15 moles per decimeter cubed. We were then given this table where we had the equilibrium concentration for the same flask at temperature T. Write an expression for Kc, the equilibrium constant, and calculate it. So remember that our Kc expression is always the concentration of products divided by the concentration of reactants, and we raise the concentrations to the stoichiometric coefficients, the mole ratios essentially. So I'm going to have my concentration of CO2 multiplied by the concentration of hydrogen. Now this is raised to the power 4 because we have 4 moles of hydrogen in our equation. Divide that then by the concentration of methane, and times that by the concentration of water, which is raised to the power of 2 because there are 2 moles of water. Now we're going to use the numbers that are in the question, the concentrations. We plug these numbers in, and it gives a Kc value of 0.025. We then have to calculate the unit for this. Remember, we have to always work out our units for Kc. And so the way I'm going to do this is think about how many mole per decimeter cubes, how many concentration terms do I have on top, and how many concentration terms do I have on bottom. So on the top, I have to the power of 1 for the CO2, to the power of 4 for the hydrogen. So that's overall kind of power 5 on the top. 1 plus 4 is 5. So we have mole decimeter cubed to the power of 5 on top. On the bottom, we have power 1 and power of 2, so overall a power of 3. And so mole per decimeter cubed to the power of 3. And so therefore, if we do this to the power of 5 divided by the power of 3, remember our rules of powers and indices, doing a division essentially is the same as taking away. So 5 minus 3 is 2. And we end up saying mole per decimeter cubed squared. And that's the same as just timesing the indices together. So we therefore have mole squared decimeter to the minus 6. So our answer for Kc is 0.025 mole squared decimeter to minus 6. We were then asked if the mixture in part B was placed in a flask of volume greater than 5 decimeters cubed and allowed to reach the equilibrium at the same temperature, state and explain the effect of the amount of hydrogen. So this, as you can see from the equation in the question, is a gas phase reaction. Therefore, we can consider how pressure affects this reaction, and likewise pressure and volume are related. They're inverse to each other. And so a greater volume is the same as a lower pressure. You can think of pressure as how potentially the equivalent of concentration, so how many molecules we have in a given volume. So a greater volume would mean that we have essentially the same number of molecules, but now in a bigger volume. that's the same as having a smaller number of molecules in the same volume. So the greater the volume, the lower the pressure. If we lower the pressure, we know from the Chatelier's principle that if we're affecting this equilibrium, it's going to shift in the direction to oppose that change. It will want to increase the pressure, and we have to look at the moles of gas on either side. Increasing the pressure means it's going to move to the side that has the more moles of gas, and this is to the right-hand side because we have 5 moles of gas compared to 3 on the left-hand side. So a greater volume, same as a lower pressure, and then using the Chatelier's principle, we can work out that the equilibrium shifts in the forward direction to produce more hydrogen. Then to explain how the hydrogen, why the amount of hydrogen decreases when it reaches the equilibrium at a lower temperature. Again, for temperature, we have to look at our enthalpy change. Our enthalpy change here is plus 165 kilojoules per mole from an endothermic value, a positive enthalpy change taking heat in. And so the forward reaction is endothermic. If I lower the temperature, the equilibrium is going to want to move in the direction that opposes that change from the Chatelier's principle. To oppose that change would be to increase the temperature, to release heat. And so to release heat is the exothermic direction. That's the backwards direction, and therefore it moves to the left-hand side, and therefore our yield of hydrogen decreases. And so a general rule for these kind of questions, when it asks you if you change a condition, how will it affect it, is always to say that, well, if the temperature change happens, if the pressure change happens, whatever it is, if X happens, the equilibrium will apply the Chatelier's principle to counter the change by shifting to either left or right, because this will reduce the heat, increase the heat, reduce the pressure, whatever it might be, to always try to explain it in simple terms. So thank you for watching this video. You can find more videos like this on my YouTube channel. If you found this video helpful, please consider leaving a review on the tuition website. And you can also check those websites out for details about how to contact me for tuition. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.